Okay, hello everyone. So first of all, I would like to thank the organizers for inviting me. I am going to talk about a joint work with Matteo Tanzi, and this is about linear response for self-consistent transfer operators. So self-consistent transfer operators, which arise from coupled map systems. Now, the history of coupled map systems goes back to the 70s, to the classical model by Kuramoto, where he coupled n-phase oscillators. So what he does in this model is he takes n-phase oscillators and randomly draws their frequencies. But then these randomly drawn frequencies are perturbed by an interaction term here, which has real constant in it, denoted by K, and this is what we call coupling strength. And the phenomenology of this model in broad terms is that for small k, we see unorganized behavior, and for large K, we see something that is called phase synchronization. And maybe this is best explained by an animation. So that's on the next slide. So these colorful circles are the phases of the oscillators, and we can see as time goes by, they synchronize nicely. So this is all I want to say about the large coupling strength regime. And for the rest of the talk, we are going to consider setups where K is very, very small. So we are kind of close to the independent system. Okay, so based on this Kuramoto model, Ly-Sung-Yang defined a discrete time coupled map system. So this can be thought of a discrete time chaotic version of the Kuramoto model, because the oscillators that are coupled in the Kuramoto model are not very complicated. But what Ly-Sung-Yang did is that she took some smooth uniformly expanding circle maps, and she coupled them with the same coupling scheme as the Kuramoto model. And what people usually do when they study the Kuramoto model is take the thermodynamic limit. So what we do here right now is we take the thermodynamic limit of Young's model. What does that mean? So that means that now we don't have just finitely many systems coupled, but we have a continuum of them. And the states of all these systems are described by a probability measure on the circle mu. And this probability measure defines some dynamics on the circle, which is the following: this map denoted by capital F. So this is just the composition of our smooth expanding circle map F and of a coupling map that is the continuum analog of the coupling map that was on the first slide for the finite case. So what's changed is that the average is just now an integral with respect to this probability measure mu. And we are going to be interested in the special case when this measure is absolutely continuous with respect to the Lebesgue measure, that's lambda here. So it has a density. In that case, the dynamics looks like this. And also, I'm going to use this notation later on for this integral term here, a psi. So if you see an a psi, this is just this integral. Okay, and so how does what I didn't say is that if you really want to think about the physical model, then maybe you should think about this probability measure mu as the distribution of, well, not colorful circles, but some infinitely many particles on the circle. And how do they evolve with respect to these dynamics? Well, you can calculate the distribution of your particles in the i+1 step as taking the distribution in the step I calculating the dynamics, what it defines, and then push this measure forward by this dynamics. So this is how the distribution of the particles evolves in time in this thermodynamic limit. And well, of course, our question is what happens as time goes to infinity. And we can formulate this problem, of course, in terms of transfer operators, because now we are dealing with measures which are absolutely continuous with respect to Lebesgue. So how do I formulate this with a transfer operator? Well, I have to calculate the transfer operator of this map, ft mu I, and push the density of, well, apply it to the density of mu I to get the density of mu I plus 1. But what is interesting here is that the dynamics also depends on mu I, which it is applied to. So this is what self-consistency is. This means that if I want to define an operator that I just simply apply to the density of psi I of mu I to get the density of mu I plus 1, it is not going to be a linear operator. It is going to be this operator, which is the repeated application of just the transfer operator of f and this operator qt. This qt operator is defined like this. So what this actually is that you take the transfer operator of the coupling dynamics with respect to T and psi, so with coupling strength T and the density psi, and apply it to psi. But like this, you can see that this is not a linear operator. Okay, so just to be clear, this operator LT, this is going to be the self-consistent transfer operator. So this is what we call a self-consistent transfer operator. And the first question that you might ask, does this self-consistent transfer operator has a fixed point? So is there an invariant density? And here I listed some previous results. And of course, all these results are for T sufficiently small. So everything what I'm going to say in this whole talk should be understood for T sufficiently small. So the first result that I'm aware of in a setup, not exactly the same what I introduced, but something very similar, is by Keller from 2000. So his setup is a bit different because the coupling is a bit different. It only operates with an integral average of the measure. And he says that if, well, all the functions that are used to define the dynamics are of a certain smoothness, then there is a unique invariant density in BV, which is furthermore of C2 smoothness. And the next result I want to mention is basically just an observation. So it is actually very easy to prove that if H is of this form, so Hxy actually only depends on the difference of x and y, such that this function has integral 0 on the circle, and f preserves the Lebesgue measure, then the constant density is a unique invariant density in C1. So we actually only proved that in this paper. This was in JSP in 2016 for a special G and for the doubling map, but it actually holds in this generality. However, this is still very restrictive. So assuming that F preserves the Lebesgue measure is very restrictive. So what we wanted to do is to make this a bit more general in 2018 with Peter Balint, Gerhard Keller, and Peter Todt. And there we used this special G. Actually, so this is the function that is used in the paper by Lai Sang-Yang too. So if you want, you can look at this as a caricature of the sine function, which is in the Kuramoto model. So basically just all goes back to the Kuramoto model. And what we proved in this 2018 paper is that if F is C2 plus, and this means that F is C2 and the second derivative is also Lipschitz continuous, then there is a unique invariant density in this smoothness class. So if we have a unique invariant density, then it makes sense to inquire about the smoothness of the mapping T to psi T. So as I change the coupling strength, does the invariant density vary smoothly in some sense? So that is what I am asking here. So again, just a very easy observation, just to make clear what I am talking about. So in our 2016 setup with Peter Balin, we have shown that this mapping is actually constant because the constant density is invariant for yes, all sufficiently small coupling strength, and it's the unique invariant density. And in the 2018 paper, we showed Lipschitz continuity in the more general setup in this sense. Okay, so you might wonder if we change the setup in some clever way, can we get more smoothness? Can we get C1 smoothness, for example? And this is where we come to linear response. And I would like to, well, remind everybody about linear response through this very simple example, which is written down in one of Vivian Baladi's papers. But it is in some sense very similar what we are going to do. So I think it would be very good to explain this. So it is well known that if we have a C2 lambda locally expanding map, this means that the derivative of F is bounded below by lambda, which is a constant larger than 1. Then we have unique C1 invariant density. So the setup here is that we take C2 path of maps, which are C3 and lambda locally expanding, plus we have this condition that the difference of the two maps in this path in the C3 norm is of order of the difference of their parameters. And we say that there is linear response if there is a first order Taylor expansion for the invariant density as a function of the perturbation parameter. And what is proved in this paper is that in this setup, there is actually linear response. So the mapping T to rho T is differentiable, and there's this linear response formula. Now you can also think of these densities, rho T, as the fixed points of the transfer operators associated to the maps FT. And what we want to do is prove linear response for for self-consistent transfer operators. So for this path T to psi T. And what are the main steps to be taken? Of course, now it is something that everyone can guess, but maybe I will just make it clear that first we have to show that we can find an appropriate setting where the invariant density is unique and where this mapping T to psi T is differentiable, and it would be also nice to compute a linear response formula for the derivative. Okay, so the first theorem is about the existence and uniqueness of the invariant density. What we show here, if F and H are C2, then for sufficiently small coupling strength, we have a unique invariant density in the space of Lipschitz functions. And this is proved by an invariant cone argument, but it can also be proved by the same methods that Keller used in his 2000 paper, because the result is very, very similar. So this is not the main novelty of our paper, this theorem, but the second one. Because the second one, well, it actually requires more smoothness from both F and H. But we state that if we have this C5 smoothness, then we get that the invariant density is going to be of C3 smoothness, and the mapping T to psi T is going to be C1 continuous from a really small interval around 0 to the space of C1 functions. And there is also a linear response formula, which is written like this. And it seems similar to the one in the theorem by Baladi. And it is actually even more similar if we look at it in a special case. So for t hat equals 0, because what happens for t hat equals 0? Well, we don't have this ugly term here, and this is just P0. So what is P0? That's the transfer operator of the dynamics with 0 coupling strength. So that's just small f, and the transfer operator of f. And what we still have to understand is what this is when t hat is equal to 0. So this is the definition of kappa t. And what we have to keep in mind, if t hat is equal to 0, then phi, which is the coupling dynamics, is just the identity, because you might remember that it was written like x plus t times something. So if t is 0, then phi is just the identity. So this is 1 here, this is the identity. And so what we are left with is psi 0 times a psi 0's derivative. And this is what's written on the next slide. So if I take the special case for t hat equals 0, I get this formula, which is very, very similar to what we have seen in the theorem by Baladi. And the reason for that, heuristically, is that if you think about it, for t equals 0, there is no self-consistency, right? Because then there is no interaction. And maybe this is the reason why we get a formula that is very similar to the setup where we don't have a path of invariant densities of self-consistent transfer operators, but just of simple transfer operators. Okay, so maybe if I still have time, I would like to say just a few words about the proof of this theorem. So what we we first do is take family of cones such as this and prove that if we choose these parameters that are the bounds on the sup norm of the derivatives, then we are going to get an invariant cone. And this is readily going to imply as the C3 smoothness of the invariant density, what was statement 1 of the theorem. But what is more interesting is the C1 smoothness of the T to psi T mapping. So for this, what we do is we define these sets of curves. So we take curves that are well defined on a very, very small interval around 0, and their values are in that cone, which was on the previous slide. Plus, there are some smoothness conditions. So we want these curves to be C2 in both variable, and we want the C3 norm of the derivative to be smaller than some K1 constant. and the C2 norm of the second derivative to be smaller than some K2 constant. And once we have this set, we define an operator acting on this set. And this operator does this. So at a point T, it gives a value to the new curve such that it takes gamma T and apply the corresponding transfer operator to it. So this is how I transform a gamma to a gamma prime curve. Okay, so I think you can see that if we have a curve that is just made of the invariant densities, so which are the fixed points of these self-consistent transfer operators, then this operator is also going to be that curve invariant. So what we prove is that if we choose our parameters appropriately, then this operator is once again going to leave this set invariant. And then by a compactness argument, we are going to get that the mapping T to psi T is actually of that smoothness. What we want is, so it is C1. Okay, and what is left is a proof for the linear response formula. And this is kind of a standard calculation, so there are no really interesting things here, just in a few words, what one should do if he wants to prove a formula like this. Well, first, we have to calculate the derivative of the operator PT with respect to T. And this is something I might not have emphasized what PT is. So just let me go back to the slide where I had that written. So here it is. So PT is the operator, which is the application of P, so the transfer operator of F and of Q T psi T. Now, what is that? So that is actually the transfer operator of the map phi T psi T. Okay. So this is what PT is, and we are going to need its derivative, and we are going to need the action of the derivative of this operator on psi T hat. And if I just write psi T hat in this ugly formula, I am going to get this nicer formula if I apply the definition of kappa. And I'm just going to memorize it. And now what one has to do is write this spectral projection formula for the invariant density. Here, phi is the C2 function with integral 1, and gamma is a small curve on the complex plane around the eigenvalue 1 of PT. So this is just a regular transfer operator of a smooth, uniformly expanding map. So we can do that, but I have to do that so that this works, this gamma works for all T sufficiently small. And I can do that because actually, we have uniform Lasotto-York inequalities for all these operators PT if T is sufficiently small. So we have a uniform spectral gap, and this works out. And what one has to do is differentiate both sides with respect to T. And while we do that and do some calculations, we plug in this formula where what we calculated here, and get this formula with a rearrangement, that formula. And to get the final linear response formula, we just have to invert this operator. And we can indeed do that for T hat small enough because PT hat, again, is just a transfer operator of a nice circle map. And yes, which has a spectral gap, and so we can of course, invert 1 minus pt hat, so we can invert this whole operator for t hat small. And then we get this formula, what was written in Theorem 2. Of course, I skipped a lot of details, but I think this is the essence of the proof. This is all I wanted to say. So thank you for the attention. And here are the references of the papers I mentioned.